Hey friend, it's Colin from SonicScholar.com. Welcome back to our C# data structures series. In this video, we're diving into the world of hash tables, a powerful data structure that allows for blazing fast insertion and search. This absolutely blew my mind when I learned about this in college. Hash tables are awesome tools, and knowing how to wield one correctly is indispensable to the craft of software engineering. But remember that every data structure has trade-offs, some things that are well suited for and others that they're not. For example, hash tables excel at providing lightning fast search capabilities on a single element, but they're not actually the best choice for things like range searches because the elements aren't stored in sorted order. In today's video, we're going to peel back the curtain on this data structure by demonstrating a very simple hash table ourselves. And then I'll show you the hash-based data structures built into .NET and Java that you should use for production tools. Building our own example will be fun and help solidify some concepts, but the data structures built into your language of choice's core libraries are much more optimized and have rigorous testing around them, so use those instead of your own. Before we get in further, I want to make sure that you have a basic understanding of object-oriented programming. Check out my C# object-oriented reference guide in the description below. I've got this here. It's just 8 pages, but it is absolutely jam-packed with everything that I could fit about object-oriented programming in just these few pages. So it's loaded with info, super concise, and I think you'll really enjoy having that as a reference. Okay, back to hash tables. First, let's talk about what a hash is. A hash is simply a number that is spit out by something called a hashing function. You can put anything you want into a hashing function, and it will give you a number between 0 and n-1, where n is the size of your hash space. One really important feature of a hashing function is that for a given input, it will always generate the same number for the output. A hashing function is an example of a one-way function because you can't take the resulting hash number and go backwards to figure out what the given input was. Put another way, for a potentially infinite number of inputs that go into a hash function, there are a finite number of outputs. So we have our hashing function, and don't worry about having to write this yourself. I have never done this, and almost all languages have a hash function that's built in that you can use. So after a hashing function, the next thing we need is an underlying data structure to store everything in. Well, once again, we find an array as the basis for another data structure. A hash table is really just an array underneath, but its power comes from 3 key things. 1, the array has a sufficient number of empty spaces and can regrow if the load factor is exceeded. 2, the size of the array is usually a prime number. And 3, a fast hashing function is used to help generate the index in the array that we want to store the object. Now, let's take a look at how this works with a simple example. Here's the scenario. Let's say this is a hash table where we're going to store some shape objects. You can literally store anything, but I just want to use shapes to make the example more abstract. I have 4 shapes that I eventually want to put in here: square, triangle, circle, and trapezoid. The first thing we need is a hashing function. The goal of the hash function is to take each shape as an input and generate a unique hash code for that shape. Ideally, the hashing function should distribute the hash codes evenly across the range of possible hash codes to minimize collisions. That is, different inputs that hash to the same output value. Take a look at this graphic. I pulled from Wikipedia, and it shows a simple example of what a collision looks like. Okay, so in our simple example, let's say we have an empty array that's 5 spaces wide. In practice, this would be much larger, but note that we're using the prime number 5 for the array capacity. Hang in there, and I'll explain why this is important. For now, consider that the hashing function generates some number that we don't really care about. What matters is we take that number, divide it by the size of the array, then take the remainder. Calculating the remainder of something is called the modulus or mod operation, and in a lot of C-style languages, it's denoted with the percent operator. Anyway, we do this because the size of the array represents the space which we're allowed to store items. And the remainder we just calculated maps to an index within the array, determining where to store the item. Let's say for our simple example, we have a hashing function that has a hash space of 16. Again, in practice, your built-in hash function will have a hash space that is billions or more, but a hash space of 16 means that possible output values of that hash function will range from 0 to 15. Let's calculate some hypothetical hash values for each of the 4 shapes. We'll say that the square gets a hash value of 7, the triangle a value of 12, 3 for the circle, and 14 for the trapezoid. Now our backing array size is currently 5, so for each of the hash values we need to divide by 5 and take the remainder using the mod function. Let's take a second and write those values down. Alright, now there's one other property about the hash table that we need to track before we start into this example. Recall that I said that one of the key properties is that the hash table can regrow if necessary, that is, if the load factor is exceeded. The load factor is simply the percentage of occupied spaces divided by the total capacity of the array. As we add stuff to the hash table, we need to be keeping track of the current load factor. If we exceed the target load factor, then we need to grow the array and rehash the contents. Don't worry, this will make sense when you see it. For this example, let's say that our target load factor is to rehash when it's over 2/3 full. So now let's start shoving stuff into the hash table, starting with the square. Its hash value was 7, 7 mod 5 is 2, so we're going to stick this in index 2 in the array. The current load factor was 0, but now it's 0.2 since 1 divided by 5 is 0.2. Next we add the triangle. Its hash was 12, which when modded by 2 is also 2. But the index 2 is already taken. This thing can happen in certain cases, so we need to be prepared for it. What we'll do is implement a simple strategy where we just keep searching along the array and find the next empty space. This is called linear probing. It's not necessarily a bulletproof strategy, and it does require you to program in some more special cases, but my goal isn't really for you to build a bulletproof hash table, it's just to understand the concepts underneath. I don't know how built-in hash sets handle collisions, but we'll pop open the source code and see if we can find out. All right, let's keep going. After inserting the triangle, the load factor is now 0.4, which is lower than our target load factor of 2/3. Next, we'll insert the circle. Its hash value was 3. 3 divided by 5 is 0 with a remainder of 3, so we'll stick this in index 3. But again, that index is taken up, so we go to index 4 and stick it in there. The load factor is now 0.6. Finally, we insert the trapezoid. What's interesting about this case is that we know that after inserting it, the load factor will increase to 0.8, which will exceed our target load factor of 2/3. So now we're going to invoke the algorithm to grow the hash table. The current size of the array is 5, and we like it when the array size is prime, so we'll pick the next prime up, which is 7. Now, I don't fully understand all the math behind this, but the way it was explained to me in college is that by using prime numbers for the size of our array, we're mathematically reducing the number of collisions that can potentially occur. So now we have to rehash all of our values and calculate the remainders for an array size of 7. Let's do that really quickly. All right, now that we have that figured out, we've got to copy the elements out of the old hash table into the new hash table in their appropriate spots. Great. Let's get back to inserting our trapezoid. The trapezoid's hash value was 14. 14, mod size of the array, 7 is 0, so we'll stick it in 0. except that the square is now there in index 0 after the rehashing operation. Take the next empty space, and we stick it in index 1. Alright, so we have all of our objects in a hash table, but now what? They don't seem to live in any particular useful order, so what can we do with them? Well, I'll show you one thing. What if I want to ask, does this array contain a circle? Well, imagine with me for a moment that our array size is in the millions. With a traditional unsorted array, you would have to start from the beginning of the array and check each element. That's potentially a million checks we'd have to do. If the array is sorted, you can use an algorithm like binary search to cut down the search time dramatically. About 20 checks are needed. But with a hash table, you simply calculate the hash value of the circle, mod by the size of the array, check the value of that index. This type of algorithm has what we call a big O notation of C for constant time complexity. Our algorithm to look up always consists of 2 steps on average. Calculate the hash, look up the index. Yes, sometimes we have to do things like linear probing, but this is an exception case, not the norm. So if it takes 2 steps to check a collection that's 2,000 elements big or 2 billion elements big, that's really powerful. All right, for the last part of the video, let's check out these data structures in C# and Java that use this type of hashing algorithm underneath. All right, so I've got here pulled up the hash set of T class from .NET, and I want to take a look in here and see what kind of strategies it uses for its hash table. I think what we'll start looking at is how does it insert elements and how does it look up things, and let's look for those special cases when something is going to hash to something that's already there, how it manages collisions. So I'm going to start by looking up the insert. Here I see there's an add T item, which just goes to add if not present. Go to that definition. Here we go. So first thing I notice here is there's a variable called buckets, and I suspect that has something to do with the collision management. Then I see something here. It's got an entry array, which just pulls from, looks like a member variable called entries. Let's look at what an entry is. What is that type? It has a hash code, so we're going to calculate the hashes once and then store it. That'll be convenient for rehashing. There is an int variable called next, which I don't fully understand yet, and then it looks like we've got a generic type T for the actual value that we're sticking in here. I'm going to go out on a limb and guess that there's something, reading this comment, something they're referring to called the free list. And I'm going to guess that that is something to deal with the collisions instead of having to use linear probing. But for now, I'm just going to hit back and we'll come back to that code. I need to understand how it works later. Looks like we've got a comparer object that's going to work for whatever generic type T that we've put in there. So either some default one, or maybe you can pass your own in the initialization or creation of this hash set. I see a variable here called collision count. That's definitely interesting. And then bucket. If I go look at what buckets is, it's also a nullable array of integers. Next we have a little block there. It says if the comparer equals null, and then else it's going to take another case. I think for the sake of simplicity, let's just look at this second block here and see what's going on. So first thing is we calculate a hash code for the value. The value is of a type T. It's a generic type that we've passed in. And we check if the value is null, it's going to get a value of 0. Otherwise, we calculate the hash code. Next, we calculate the bucket that the hash code corresponds to. If I go to that definition, we can see looks like 64-bit machines. There's a fast modulus operator, but you can see what it's doing for 32-bit. It's take the hash code, mod the length of the bucket. So that looks really similar to what we've already looked at. We come back here and now we have a bucket number, and apparently the buckets is 1 based instead of 0 based. That's kind of interesting. And that's going to be what I is. And funny enough, we're going to have a loop that says as long as I is greater than or equal to 0. The first thing I'm immediately looking at is how do we get out of this loop? If I is greater than 0, Well, it looks like the only place that might happen is this return. So we'll look at that case. And then there's also a situation where I is set to entry.next. So it almost looks like a linked list type of thing. So whatever this case is, sometimes entry.next is going to be negative. And recall, we took a look at this structure here, and there are situations where this may be negative. And so it looks like in this algorithm, we've got cases where this will be negative to be done with our while loop, and then we know when to kick out. So while I still don't know what the free list is, I'm just kind of taking my high-level knowledge of hash tables and using that to make some educated guesses. But let's keep going back. Looks like the first thing we do is using that bucket we calculated, we grab an entry out of that array. So we've already done the hash code calculation. Now we're just grabbing the entry at that spot. So I guess then what we do is we take the hash code we just calculated, compare it to the hash code that was in that entry we just pulled out. And if they're the same, and this comparer equals function determines that they're already the same, then that means we're trying to insert something that's already in the list. And so we can just return false for this whole method. So then it looks like at some point the entry.next will be negative. We'll kick out of this loop. It looks like some kind of corner case they're just covering for. And we've got case about the free list. Again, don't understand too much about that, but I can scroll down here and see, there's a resize that happens. Maybe go check that out, see what's in there. See that this resize calls a helper method that is called expand primes, which I can't get to under here, but I can just imagine, given the current count of the size of buckets or whatever, this is probably picking the next biggest prime. So that's kind of interesting. This appears to potentially be rehashing the codes if it needs to, or maybe using the cached hash codes that it already has, recalculating the modulus and all that good stuff, and tossing stuff back in the new, just kind of like we did. This section here appears to me about where they're actually storing the value. So we take the hash code we calculated, throwing that into the entry, updating its next value, which is the bucket that was calculated, and then actually storing that t value into that entry as well. Updating the version, I guess that just lets it know every time it's modified, that version can increase, and storing the location at the index. So admittedly glossing over a lot of stuff that's here, but can kind of use the high-level concepts that we covered, and if I really wanted to, I could dive down a little bit deeper and figure out how this is working. Next thing we could go look at is the contains method. So we have our item, type T, and it just basically says find the item index. If it's greater than 0, then it contains. And so we can go look up here. There's our item that's passed in. Very similar to the add code that we already looked at. Grab the buckets, grab the entries. I'll collapse this comparer case and look at what we have here. It looks very similar. Calculate the hash for the item. If it's null, then it gets 0. Get that bucket, and here a similar loop again. We have while I greater than equal to 0, trying to find if that item exists. If the hash code we just calculated matches the entry's hash code and the comparison, this equals method determines that they are equal, then we just return that index. I'm guessing then that if this comparison determines that they're not equals, but the hash codes match, then this could be the example where there was a collision that happened, right? So here's our collision count. So what we do is we set I is the next entry, and we just loop through here again, pull out this entry, and keep going. And then I would guess that once that entry has a next value of -1, it means that it's actually not in the list. So this kind of is like linear probing that we talked about. It's just using a little bit different way about it. And so if the item isn't in here, meaning we kick out of this while loop, then the item's not in the hash set at all. And we can just return a -1 index to say that it's not in here. As we look at the comments here, it says get the index of the item in entries or -1 if it's not in the set. And so the helper method for contains just checks to see if it's greater than or equal to 0. So looking at the code already really helped me zip through this and see what was going on quite a bit faster. So here we are in Java looking at its implementation of hash set, and let's see if there's any similarities. Right away, I noticed that it has a hash map underneath, and so it looks like it might be actually using another data structure hash map to implement the hash set, which is kind of to me, that seems like a cheater shortcut way to do it. So we'll probably have to go in and look at the hash map class. Scroll down here and look at contains, and all it's doing is checking if the hash map contains key. So it's just delegating all that stuff. Same thing with the add. It's returning, it's using the maps put method to add it there. So clever. Why reinvent the wheel twice if you don't have to? So let's go look at the hash map. Okay, so we're in the hash map, and check this out. They've got a load factor here. If we take a look at that, if I hover over it, it's a constant, and it looks like 3/4 full they're using for their load factor. Looking at that contains key that the hash set was using earlier, it's just delegating to get node. So why don't we go look in there? We have an object for the key that we're passing in. This definitely looks a little bit more dense than what we looked at with .NET. So let's see if we can find out what's going on. Looks like our node is some kind of key value pair. Got value for tab, first, variables for n, hash, and k. Yeah, so definitely very dense. Tab must mean table. And I'm not even going to pretend to dissect this in a meaningful way in the amount of time that we have left for this video, but I'm going to look and see. We've got a hash calculation happening. Let's take a look at that. Yeah, based on the object key, there is the hash code function. So that's built into Java Lang object. So that's what it's using for hash calculation. That's stored in this hash variable, and then looks like we're checking for if a hash is equal to the hash we just calculated, and making sure that there is some equality so that the object is there. So that actually looks pretty similar to what we saw in the C#. We've also got this next variable. So it seems like there is some kind of chaining way to handle collisions. Pretty similar approach, I would guess, which makes sense because this problem has probably been solved by very smart people, and they know the optimal way to handle this. Not sure what they're using a tree node for. Maybe this is like a linked list. I'm not really a Java guy, but I could just imagine they're using this for some kind of probing technique. This while loop looks similar. Look, it's a do while instead of a regular while, but look, get the hash, check the key, check equality. If all that matches, then we just return E, and we're in this while as long as E.next is not null. So in .NET, they were looking for checking for next was a integer and making sure that it was greater than or 0. So to me, this looks like a very similar approach, just implemented a little bit more different and a little bit more concise. And if we don't find it, we kick out of that loop and it just returns null. So check this out. When we're asking, does this thing contain a circle? Get node. And if it's not null, then it does contain it. Or if it is null, then it doesn't contain. So very cool. A similar thing here, we've got put and put val, which I'm guessing if I look in here, this is going to be pretty similar. I'm going to just gloss over this again for the sake of time, but looks like there's bins or buckets or whatever they're calling them in here. There's going to be code to handle the collisions and stick things on some kind of floating list. So pretty cool. Again, not going to dive in super. If you want to, you can look at hashmap.java in the Java Lang API. I will draw quick attention. Looks like after inserting something, we've got our resize method. So I'm curious to see if they're going to use primes again. And I don't think they are using primes, not that I can see offhand. As I look here, we've got a couple constants here. Maximum capacity, that looks like some power of 2 to the 30th. perhaps. But if you look at the default initial capacity, that's actually 16. And it's interesting that it says it must be a power of 2. And when they want to resize, looks like here the new threshold is they take the old one, bitwise shift it over by 1. That's essentially just saying times equals 2. And then that becomes the new threshold. So once that is increased, looks like those tree node data structures that they've got to traverse through those and get those into the hash table as well. Again, not even going to pretend to dissect that quickly, but interesting to just peek my head in here and see what's going on. Now, as we wrap up, let's recap some of the big ideas. Hash tables are great for lightning fast single operation lookups and quick insertions, but if you need a range search, for example, get me all the strings from letters K to M, a hash table will be no use to you. You're better off storing your stuff in a data structure that sorts objects in order, since hash tables don't store them in sorted order. Quick reminder, I've got that free guide for you to grab if you're programming in C# or even in Java. I've condensed all the most important object-oriented concepts into an 8-page reference sheet. You'll learn the 4 pillars of object-oriented programming: classes, structs, objects, interfaces, abstracts, generics, static, access modifiers. It's all just packed in here for you. Yours for free. Just check out the link in the description. That's all for now. I've got a parting challenge for you. I've described a simple hash table algorithm, and we've looked at some API code. Why don't you try implementing a hash table and let me know how it goes? Leave me a comment if you got any other questions. I'll be happy to read it and get back to you. Thanks, friend, for watching, and I'll look forward to seeing you in the next video. Take care.